296.32. Okay, that is your point. Okay. So we know that we are going to get the complex conjugate roots. So the general solution, student asked me, do I provide general solution in the formula sheet? Yeah, I'll provide the general solution. Okay, I don't expect you to memorize this at all. So the general solution that we're going to use is x as a function of t is equal to e minus alpha t C1 cos omega t plus by C2 sine omega t, right? So remember, what is alpha? Alpha is equal to C over 2m, and beta is equal to C squared minus 4mk over what? 2m, right? So now, another term that we know, or before I go on, anyone have any questions so far? Are we okay? Yes. Say it again. Yeah. Yep. Because it has complex conjugate roots. This is by determined from here, right? C squared is equal to 0. So what is the interesting bit is this. Alpha is equal to what? 0. Yes or no? You don't have C over 2m. So exponential of 0 is equal to what? 1. So your solution now, right, looks like this. So you know the solution now is x as a function of t is equal to C1 cos omega t plus by C2 sine omega t. To me, this is real intelligence, not AI. Can you see the difference now? This is what? Real intelligence. An exponential function to the power of 0. The whole thing, the decay function just got removed. The coefficient becomes what? 1. Right? That's why they say mathematics is the real intelligence. Why do we create artificial intelligence? Any idea? What are we teaching you over here? Real intelligence. Are we clear? Okay. Sorry, you don't get the humor yet. Maybe later on you will. Right. So another term to remember is omega now is equal to what? Omega is equal to, I wrote something about omega earlier. Omega is equal to 4mk. Is it 4mk? Yep. I forgot what I wrote about omega. Omega is equal to square root of 4mk minus c squared divided by what? 2m. Okay. Now, we are going to focus on omega now. Which is equal to square root of what? 4mk minus c squared, okay, divided by 2m. So for our case, we're going to substitute c is equal to 0 because in our example, what we have is the what? Is the damping is equal to 0. So therefore, the expression now becomes 4m k over 2m. And if I introduce the entire term, square root the whole term, so it will be 4mk over 4m squared, right? So I can cancel this, I can cancel this, I can cancel this, I can. So this will be equal to square root k over m. And this over here is also known as omega n. And omega n stands for undamped natural frequency. Okay, it's known as our undamped natural frequency. Now, what will happen when a system operates at natural frequency? Any idea? Why does a glass, a drinking instrument or drinking utensil made of glass breaks when it reaches a certain frequency? Any idea? Because if the frequency that we impart onto the object reach is what? Natural frequency. So what happens to the system when it hits its natural frequency? What happens? So the next one, the next graph I'm going to draw is what's going to happen. Okay, so what we have, the graph over here. Okay, x-axis is frequency, y-axis is amplitude. Okay, so you'll see a system response. It will peak and die down. And when it peaks, okay, this is what we call our omega n. Have you experienced anything like this before? In at least once a week, that you feel something reaching its natural frequency. So what do I mean? Okay, once a week, and I'd like to elaborate at least once a week. You will see the vibration not doing anything. It will peak, and then when it go faster, it will come down. Where have you seen a system like this? Anyone? You all do laundry? Cheeky sort. Do you all do laundry? Yes or no? Right? You don't see it in your washing machine at all. Your washing machine, nothing. But when you put in the dryer, what happened? Doom, 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 doom. Then when it go faster, all of a sudden the vibration what? Dies down. You do laundry, or is it just me? Right? So when you go like you know, when sometimes when things start to vibrate, people say stop. But as mechanical engineer, we say no, go, yes or no? This is the reason. But be careful, okay? Don't overquote me, okay? So you see yourself, you reach to a maximum amplitude. Imagine if you go up here and it start to vibrate, you panic, what happened? You switch off the machine. No. What do? Let it go. Okay. So when it goes faster, once it's reached its resonant frequency, when the frequency down here can be RPM, rotation of your system. Okay, now my car, Mazda 3, 10 years old, at 2,500. Pardon my French, I say like, don't care about the vibration. When it starts to vibrate, either I go faster or you go what? Slower. Don't be stupid enough to stay at 2,500, okay? Right? You either go faster or slower. So when you've been caught speeding, you tell the police, I have to go faster. Okay? Or not, my car keep on vibrating. Okay? Okay. Again, dark humor. Anyway. So now we know that omega n is equal to square root k over m. Okay. So this will be equal to square root of 890 over 9.072. and omega 890 is 9, okay, 899.072 square root 9.905, and this is in radians per second. Okay. So now we don't have too much to go. Okay, so we know x as a function of time. So this one is equal to C1 cos 9.905 t plus by C2 sine 9.905 t. Okay, and this is our general solution. Okay, so what do we know? Okay, so we're going to impose boundary conditions. Okay, we're going to have two boundary conditions. So the boundary condition I'm going to have is when x at time 0, this will be equal to 0.15 meters. And the velocity is equal to 0 meters per second. Okay, I'm just going to, after the load has been suspended by the spring, you know there's an extension of 0.1. So that's the new equivalent. I stretch it to 0.15 meters and then I let it go. Okay, basically that's what is going on. Now, when velocity is equal to 0, right, means I'm just going to let it go without moving my head. If I put a velocity, it means I will do an upward push or a downward push. Be clear? Okay, but for this case, we are going to release it at speed equal to 0. So from now, from here, we can determine C1 and C2. Okay, so you substitute when x of 0 equal to 0, so the expression over here, so this will be equal to C1 cos 9.905 multiplied by 0, then plus by C2 sine 9.905 multiplied by 0 again. Okay, so sine of 0 is equal to 0. So this will be equal to, oh, sorry, this is 0.15. My apologies. So 0.15 is equal to C1. Okay. Then from here, we differentiate dx by dt. Right? Why we have to differentiate? Because our next boundary condition is what? Is velocity based. So minus, I think you guys can do this really well. I'm almost done. Okay. Sine 9.905 t plus by 9.905 cos 9.905 t. Okay, so we know that this is, we're going to substitute x dot 0, the whole thing is equal to 0. So we know that this is 0 sine. I think something is missing down here. I think I have my C1 missing and I have my C2 missing. Okay. So down here we'll have my C1, and then down here my missing is my C2. Okay. So from here, this will be equal to minus 9.905 multiplied by C1 is 0.15 sine of 9.905, the whole thing multiplied by 0. So this term over here is equal to 0. Plus by 9.905 multiplied by C2 cos right? 9.905 multiplied by 0. So the whole thing, C2 is equal to what? 0. So to end this, x as a function of time, this is equal to 0.15 cos 9.905 t meters. Okay. So very interesting. Without the damper, the decaying function just disappears. So if we're going to sketch this out, okay, it's cosine. So this is just a sketch. Okay, this is your response. Oi! So this is your time, and this is your x. Okay. Hey, I appreciate you guys being here. Have a good weekend. Be safe and be good. Are we clear? I want to see you next week. Okay. Now, those of you online, bye-bye. Are you okay? You're okay then. Okay. I'll stop record. I will post the recording online. Okay. Yes. Okay.
Is the M for on beside the T? That.
Meters.
Oh, okay.
Unit.